Good day everyone, I am Gemmalyn L. So today, I am going to discuss the source transformation. So first, I am going to define the source transformation, discuss the process or steps when applying the source transformation, and also let's solve some problem applying it. So now, let's define the source transformation. Source transformation is the process of simplifying a circuit solution, especially with mixed sources, by transforming the voltage sources into current sources, and vice versa. Definitely using the Thevenin's theorem and Norton's theorem respectively. Also, source transformations are not limited to resistive circuits. They can be performed on a circuit involving capacitors and inductors as well, by expressing circuit elements as impedances and source in the frequency domain. In general, the concept of source transformation is an application of Thevenin's theorem to a current source or Norton's theorem to a voltage source. However, this means that source transformation is bound by the same condition as Thevenin's theorem and Norton's theorem, namely that the load behaves linearly and does not contain dependent voltage or current sources. So, it says there, if we saw a voltage source, we are going to transfer it to a current source. However, if we saw current source, we are going to transfer it to voltage source. So how are we going to transfer it? So using the Ohm's law. Here are the formula of Ohm's law. So I is equal to V over R and V is equal to IR. This formula I is equal to V over R. We are going to use it if we transfer voltage source to current source. Also, this formula V is equal to IR. We are going to use it if we transfer current source to voltage source. We have an example here. As you can see, this circuit is example of a voltage source. So we are going to transfer it to current source. So using the formula IS is equal to VS over R. So now we are going to compute the current source. So IS is equal to the value of Vs, which is the 5V, over the value of R, which is 25 ohms. So now let's divide the 5 divided by 25, which is 0.2 amperes. So now the value of current source is 0.2 amperes. If we are going to transfer it to current source, the current source would be like this. Now, we have current source here. So we are going to transfer it to voltage source using the formula of Ohm's law, which is Vs is equal to ISR. Vs is equal to the value of Is, which is 2 amperes, times the value of R, which is 25 ohms. So, Vs is equal to 50 volts. So, the value of the voltage source is 50 volts. So, if we are going to transfer it to voltage source, the voltage source would be like this. That's all for the source transformation. I hope you understand and you learn from it. So once again, Good day everyone, I am Gemmalyn L. So today I'll be going to discuss the Norton's theorem. So first, I am going to define Norton's theorem and give some key points when applying the Norton's theorem, also the step or process, and let's solve another problems applying the Norton's theorem. So let's define it. Norton's theorem states that any linear circuit can be simplified to an equivalent circuit consisting of a single current source IN and a parallel resistance with a resistor RN that is connected to a load. Norton's theorem is similar to Thevenin's theorem in that it allows us to simplify any linear circuit to an equivalent circuit. However, instead of using a voltage source and a series resistance, the Norton equivalent circuit consists of a current source with a parallel resistance. Applying the Norton's theorem to simplify a network can make it much easier to evaluate variable loads. So for example, you have linear two-terminal circuit and this circuit is either simple or complicated. Then you have RL load across it and let's say A and B. Therefore, we are going to use the Norton's theorem to convert this linear terminal 2 circuit into equivalent single current source IN with a resistor parallel to current source which is the RN or the Norton's resistance. So if we are going to analyze this circuit, we are able to use the current divider to find the current in RL. So we will use this formula which is the IL is equal to I all over by RL all over by RN plus 1 all over by RL times IN, or simply we can use this formula RN all over by RN plus RL times IN. To get the voltage across RL, we're gonna use the formula of Ohm's law which is the VL is equal to IL times RN. Here are the steps on how to find Norton's current and Norton's resistance. As with Thevenin's theorem, everything in the original circuit except the load resistance has been reduced to an equivalent circuit that is simpler to analyze. Like Thevenin's theorem, the step used in Norton's theorem to calculate the Norton source and Norton's resistance will be generally similar. Step 1. Remove the load resistor. The first step is to identify the load resistance and remove it from the original circuit. Step 2. Calculate the Norton current. To find the Norton current, place a direct wire connection between the load points and determine the resultant current. Note that this step is opposite the respective step in Thevenin's theorem where we placed the load resistor with a break and calculated the voltage. Step 3. Replace the power sources. To find the Norton resistance for our equivalent circuit, we can now replace the power sources from our circuit. The voltage sources are replaced with short circuits and the current sources are replaced with open circuits. This process of replacing the power supply is identical to that used for the superposition theorem and Thevenin's theorem. Step 4. Calculate the Norton's resistance. After replacing the two voltage source, the total resistance measured at the location of the removed load. Step 5. Draw the Norton equivalent circuit with the Norton current source in parallel with the Norton resistance. The load resistor reattaches between the two open points of the equivalent circuit. So here is the example applying the steps of Norton's theorem to a linear circuit. So applying the first step, identify the resistance which is here and remove it from the original circuit. And now this is the circuit. Next step is to find the Norton current. Since the node between R1 and R3 is now shorted to negative terminal of the both batteries. So using the Kirchhoff's current law or KCL, we know that IS is equal to I R1 plus I R2. So now applying Ohm's law to each of the individual branch current, we have here IS is equal to I R1 plus I R2 is equal to V1 all over by R1 plus V2 all over by R2. Using this formula, so we can now solve for the short circuit current. So, Norton current is equal to V1 all over by R1 is plus V2 all over by R2. So, that's the formula for getting the Norton current. So, now, IN is equal to the value of V1 which is 28 volts all over by the value of R1 which is 4 ohms plus the value of V2 which is 7 volts all over by R2 which is 1 ohm. So now 28 divided by 4 is equal to 7 plus 7 divided by 1 is equal to 7. So the Norton current is 14 amperes. So the value of Norton current is 14 amperes. Next is find the Norton resistance. The Norton equivalent resistance is calculated as Rn is equal to 1 all over by 1 over by R1 plus 1 all over by R3. So, copy the 1 all over by the 1 which is the value of R1 is 4 plus 1 all over the value of R3 which is 1. So, 1 divided by 1 over 1/4 4 plus 1 over 1 is equal to 0.8 ohms. So the value of Norton resistance is 0.8 ohm. So this is the figure of the Norton equivalent resistance circuit. Lastly, here are the drawn Norton equivalent circuit. In this figure, I reattach the 2 ohm load resistor from the original circuit. And that's all for the Norton's theorem, and I hope you learned from it. Thank you and God bless.